Hey all, this is Mr. Bergman here with section 6.5, Operations with Radical Expressions. I'm glad you're with me. Let's get right into it. So, you might remember back in section 6.3 where there's a even odd rule that I tried to teach about absolute values. Well, today we're not going to need them. We could use them, but there's actually in the problem set that we do in class, it's going to say that assume all variables represent positive numbers or something like that, and it just means that you don't have to worry about adding absolute values. We could if we wanted to, but the instructions are not making us, so we're not going to do it. That's what the FYI for today is. Let's do a review. So let's simplify the square roots. If you get a square root of 50, we know you can actually separate that out into the square root of 25 times the square root of 2. 25 times 2 multiplies back up to 50, so you're allowed to do that. Why would you do that? Oh, it's because you can actually simplify the square root of 25, and you get 5. And 5 root 2 is actually what we're going to call simplified, or more simple than square root of 50. Let's do that again here. Square root of 32. Well, you can't really take the square root of 32, but you can factor out a 16. 16 times 2 is 32, and you can actually take the square root of 16. This is what I like to call perfect square factors. 25 and 16 are both the perfect square factors of the numbers that came before them. And they're great because you can simplify them. So, with that being said, I'm going to call this over here. We're going to actually generalize this to not just have numbers, but with variables also. So I'm going to call this the perfect power, and it's going to be in red every time for this entire lesson. And then this blue over here is the leftover factor. It's not a perfect power. It's just 25 times 2 is 50. 25 is the perfect square, and 2 is the leftover factor. 16 is the perfect square, and then 2 is the leftover. When I say perfect power, I mean the thing that is that will eventually simplify. Square root of 16 eventually simplifies to 4. Square root of 25 eventually simplifies to 5. So let's take a look. So here, as we can see, as we've seen already, 25 times 2 separates into the square root of 25 and the square root of 2. We're going to use this fact. We're going to use the similar fact when it comes to fractions. You can split them up and put them in two different radicals. And then we're also going to use this fact as well. The square root of, or not the square root, the b root of x to the a is going to be the same thing as a over b. It's particularly useful when a over b is a fraction that simplifies, like 10 over 5, or 6 over 3, or 9 over 3, or whatever it is. When that fraction simplifies, then it's going to be really great, like this over here. The cube root of x to the 6th is the same thing as x to the 6 over 3, because the cube root turns into the denominator. And then we can actually simplify this fraction. It's just x squared. So another way of thinking about this would be, what variable times itself 3 times gives you x to the 6th? And the answer is x squared. So anyway, x to the 6th is a perfect cube because you can simplify x to the 6th, the cube root of x to the 6th. 8 is a perfect cube, 27 is a perfect cube, 64 is a perfect cube, 125, those are all perfect cubes because you can take the cube root of them. And so x to the 6th is a variable representation. The cube root of x to the 6th simplifies to x squared, as we saw. Now, so if you just had the cube root of x to the 6th, then we'd be able to simplify that, no problem. Just like over here, if you had the square root of 16, it simplifies to 4. But if you had the square root of 32, then we have to figure out how to simplify that. And this is what it looks like. So x to the cube root of x to the 6th is one thing, but the cube root of x to the 8th, you can't, 8 divided by 3 doesn't simplify because it's like 2 2/3 if you're going to try and divide 8 divided by 3. And so instead what we're going to do is we're going to factor it out. Here's the red-blue combo that I was talking about before. There's a perfect power and a leftover factor. X to the 6th is a perfect power. It's actually a perfect cube. And then the leftovers would be x squared because 6 plus 2 is 8. Okay, so we can actually simplify the red part. It turns into x squared. And then the cube root of x squared is over here. And this is the leftover factor. Red, blue. This is red simplifies and blue is the leftover, and it stays. That's what that's going to look like, and we're going to do it quite a few times coming up. So let's take a look here. Let's say you had to simplify the square root of 75 and x to the 12th and y to the 7th. Well, looking at this, you can actually take this. You are able to take the square root of x to the 12 because 12 divided by 2 is 6. That simplifies. 12 over 2 simplifies to 6. But 7 over 2 doesn't. And that's good to know. And the square root of 75, I got the feeling we can do some of this business over here. So I like to kind of check to see which of these are going to be perfect powers. And it looks like the x will be perfect power, but the y is not. Then I like to split them into factors. You can see here, this gets, I wonder if I can just move this down a little bit. Is that better? That's a little better. That's what I really want to say. So now I'm going to split this into factors. We can examine the 75 and the x and the y individually from each other. I'm going to split the 75 into, even to square root of 25 and square root of 3, because there's a perfect power here. I should have made this red. This is square root of 25 is a perfect power, and the square root of 3 is a leftover factor. Sorry, I couldn't help myself. Okay, so this is the perfect power, and this is the leftover factor. And this is also a perfect power, and this is a leftover factor, because y to the 6th times y is y to the 7th. I'm going to simplify that out, or remove it, because it's a perfect power, because I can actually simplify square root of y to the 6th. What variable times itself is y to the 6th? Well, it's just y to the 3rd. Y to the 3rd times y to the 3rd gives you y to the 3rd. That's why, so when you take the square root of y to the 6th, you get y to the 3rd. All right, so now that I have this, I'm going to I can actually take the square root of 25, and that's 5. I can't do anything with the square root of 3. That's a leftover factor. It's just like square root of y is a leftover factor. I actually can take the square root of x to the 12th. What variable times itself is x to the 12th? It's x to the 6th. There it is. And so I'm simplifying the perfect power. And I'm going to simplify this perfect power also. So now I have these 1, 2, 3, 4, 5 different things that are all being multiplied by each other because they're all separated with multiplication. And I think what I'm going to do is just combine them together. This square root and this square root, I'm just going to put in one big square root, 3y. I'm going to throw it at the end, and everything else is going to get moved up to the front. And that way, it's incredibly clear and obvious, what is inside the square root and what is not. Textbooks and websites and stuff always like to put the square root last, so that we're absolutely sure that only the 3y is in the square root and not anything else. If you were to put the square root first, then you'd be like, is that 5 inside the square root? Maybe it is, maybe it isn't. That's just how we do it. All right, so let's do the same steps again. I'm going to check to see whether or not these things are perfect powers, and or not. Except it's not square root anymore. It's the 4th root. It's going to be a quartic root. So, looking at this, 5 divided by 4. Can you actually simplify that as a fraction? No, you can't. 5 divided by 4, that'd be something tricky with the remainder. But 20 is divisible by 4, so y to the 20th is a perfect factor. Okay, so here we go. We're going to split them all up. The 4 gets its own 4th root. The x gets its own 4th root. The y gets its own 4th root. And in fact, I'm going to split the x into 2 different 4th roots, or quartic roots. X to the 4th, which I like because I can simplify that. It's a perfect power. And x to the 1st, which is not. So then I'm going to actually simplify. I can't take the 4th root of 4, but I can take the 4th root of x to the 4th. What is that? It's just 1. Now here's an even odd situation, 4, 4, 1. And if those instructions weren't there, I'd be required to put an absolute value. But we don't care about that right now because of the instructions we have that's saying all variables are going to be positive. So we'll just write normal x. We can't take the 4th root of x to the 1st, but we can take the 4th root of y to the 20th. What times itself 4 times? What variable times itself 4 times is y to the 20th? It's y to the 5th. And here's another even, odd situation, which we are not required to put absolute values on. Let's see. We're going to simplify and combine these things. So x and y are all going to go in the front, and then the 4th root, and then everything that's inside of the 4th root will be here. And this is nice and easy thing to type up. Okay, so what I really want to say is that this line right here is technically allowable in ALEKS.com. If you were to type this in character for character, all separated by multiplication, you'd get the question right. However, this is a little bit easier to type in, and it's kind of like how formatting works in textbooks and that kind of thing. So we're gonna take it all the way to this step. cube root of 24, a to the 6 over 125. Well, we're going to split them up. The fractions get split up, and the different factors in the numerator all get split up. So the 24 and the a and the 125, they all get their own cube root. And now we can kind of ask ourselves, which of these can you take the third root of? Well, I can't take the cubic root of 24, but I can find a perfect cube that does a perfect cube factor of 24, and that's 8. So I'm going to split that 24 up into the 8, which is the perfect cube, and the 3, which is the leftover factor. I can take the cube root of a to the 6. What variable times itself 3 times is a to the 6? It's just a squared. Times itself 3 times is 8. So I take the cube root there, and then the cube root of 125 is 5. We're going to simplify the cube root of 8 to get just 2, and I'll put the a squared in front just so there's absolutely no confusion as to whether or not it's like here. If you were actually handwriting it with a pencil, I'd be like, I don't know, is that a squared inside the cube root or is it outside? Definitely outside when you write it in front first. All right, next one. Ooh, there's a whole lot going on here. I think what I'm going to do first is I see there's an x in the top and x in the bottom. I'm going to simplify those first. 8 minus 2 is 6, and so it's x to the 6th. And then I'm going to split these up. The 9, the x, the y, and the 25 are all going to get their own square roots, just so it's a bit, divide and conquer kind of a deal. We can take the square root of 9. We can take the square root of x to the 6th. We can take the square root of 25th. We can take the square root of y to the 13th. But you can split it up into a perfect square and a leftover factor. The perfect square, the largest perfect square is y to the 12th, and then there's a leftover of y to the 1st here. So that when you do take the square root of y to the 12th, you get y to the 6th. Notice, even 2 is even here, so even, no, let's see, even. Where was it? Oh, yeah. Even 6, 2, the unwritten 2 is also even, and this is odd. And if those instructions weren't there, we'd have to apply the absolute values, but we don't, so it's cool. And this is our answer right here. Notice that the square root is towards the end. All right, let's flip the page. And while I do, I'll just throw it out there that my favorite Philly cheesesteak, there's all sorts of lovely cheesesteaks out there, but my favorite Philly cheesesteak is the pizza steak. Pizza, you heard it here. That's my favorite. Why don't you tell me what yours is when you come into class tomorrow? All right, we're going to simplify by multiplying by radicals. So here we got this ugly honkin' mess. Look at all that stuff here. I think because this is a fifth root, a quintic root, and this is a fifth root, quintic root, we can multiply these two together and combine some things. So that's what we're going to do. As a preliminary step, we're going to multiply both of these together. 4 times 3 is 12. This fifth root and this fifth root, we're going to multiply everything inside. So negative 10 times 16 is negative 160. X squared times x to the 4th, that's 2 plus 4 is 6. 6 total x's being multiplied by each other, and then there's a total of 10 y's as well. All right, so now we're just going to keep on doing what we did before on the previous page. We're going to split up into factors. The negative 160 gets its own fifth root, the x to the 6th gets its own fifth root, and the y to the 10th gets its own fifth root. And then we're going to start thinking about it. So check this out. I can see right off the bat that the y's is going to be pretty straightforward to simplify because 10 over 5 is 2. What times itself 5 times is y to the 10th? Y squared. 10 divided by 5 is 2. Not so easy to do over here. It would be way easier if it just said x to the 5th, because 5 divided by 5 is 1. So that's in fact what I'm going to do. I'm going to split up this x into x to the 5th times x to the 1st. And so this red thing is going to be easily simplified, and the blue one will not. Same thing here. Fifth roots. The 2 times itself 5 times is 32, and since 5 is an odd number, I can even pull out the negative. So negative 2 times itself 5 times is negative 32, and that is a pretty large number that I can pull out, and the leftover factor is 5. So now I've got all these things here, and I can simplify the red ones, and so this becomes negative 2, and this one just becomes x. This one becomes y squared, and the others, the blue ones, stay the same. Bringing the 12 down for the ride, you can actually combine the 12 and the negative 2 to get negative 24 x y squared. And then combining the fifth roots, you just get 5x at the very end. And that's what we get there. here we're gonna do the same process again. First step, preliminary step, is going to be multiply these two together, so we just have one thing. Negative 9 times 9 is negative 81. X to the third, x to the fourth turns into x to the seventh, and then y to the fifth times y to the fourth is y to the ninth, because you add the exponents. Okay, so now third. Let's see, which of these is divisible by 3? 9 is divisible by 3, but 7 is not. So I'm going to split these up for the very first step, is I'm going to split them up. And now we can see that you can consider them all individually. And y to the ninth, the cube root of y to the ninth is going to be, we're just going to keep that there. I think we'll simplify to the next step. Negative 81 is not a perfect cube. There's no one thing times itself 3 times to give you negative 81. But I do know that 3 times itself, or negative 3 times itself 3 times is negative 27. So I'm going to factor that out, and the leftover is 3. Similarly, 7 divided by 3 is no easy number. It's no integer number, at least. So, but I can do 6 divided by 3. That'll be easy to do. I'm going to factor out x to the 6th, the perfect cube, the perfect power over here, and then the leftover factor is x to the first. 6 plus 1 is 7. 1 is left over. I'm going to simplify the red. It turns into negative 3, and this one turns into x squared. And you can see that the blues they remain untouched, and then I can actually take the cube root of y to the ninth, it's y to the third. I'm going to simplify and combine all these together. 5 times negative 3 is negative 15. The x squared y cubed go here, and that cube root of 3x goes over here. Here, let's do this whole process one more time. We're going to multiply the square roots to get 256 a to the 10th, b to the 7th. We're going to break them up, so we're just looking at these all, considering these individually. A square root of 256. I think we can actually take the square root of 256. We can take the square root of a to the 10th, but we can't take the square root of b to the 7th very easily. We could take the square root of b to the 6th easily, because 6 divided by 2 is just going to give us 3. The leftover factor would be b to the first. So there it is. 2 goes along for the ride. Square root of 256 is 32. Square root of a to the 10th is 5. Even, odd. This would have to have an absolute value, except the instructions say we don't need it. Same thing here. Even, odd. There's an unwritten 2 here. And then the blue, b to the first, square root of b to the first just goes along for the ride. Collecting everything. Oh, this should be 64, a to the 5th, b to the 3rd, times the square root of b. All right. So next, add or subtract by combining like terms. All right, so we're going to have to split these things up here. 40 square root of 45x, we can split that. We can factor out a square root of 9. That'll simplify. What's the perfect square factor of 12? It's 4. The leftover factor is 3. And what's the perfect square factor of 20? It's 4. The leftover factor being 5x. We can simplify everything that's red. And when we do, we get 3 times 6 is 18. We get 2 here, and we get 2 times 3 is 6. Notice we've got some like terms. The square root of 5x, the square root of 5x. There's 18 of them here, and then you subtract 6 of them to be left with only 12. Square root of 5x's plus 2 root 3 goes just continues and goes down along for the ride. Here, square root of 18x minus 5 root 28 minus 3 root 98x plus 3 root 7x. Whew, so much going on. I think I spot some perfect square factors. In 18, the perfect square factor is 9. In 28, the perfect square factor is 4. And in 98, the perfect square factor is 49. These are all the red things are things we can simplify. And when we do, it looks like this. 3 root 2x minus 10 root 7 minus 21 root 2x plus 3 root 7x. Now, hold your horses here. You might be excited to combine this root 7 and this root 7x, but there's actually not like terms because of the x. The only like terms that we can combine are these root 2x's. There's 3 of them here, and then you subtract 21 of them here, leaving you with minus 18 of them. So So this is what your answer is. Negative 10 root 7 minus 18 root 2x plus 3 root 7x. One last one for the road. 2 root 48 minus root 75 minus root 12. Let's see. Well, the perfect square factor of 48 is 16. Perfect square factor of 75 is 25. Perfect square factor of 12 is 4. And the leftovers are all root 3. All of them. So when you simplify the red parts, you do get 4 times 2 is 8, 5 from the 25, and 2 from here. You've got 8 of these minus 5 of these minus 2 of these. It's kind of like saying, 8x minus 5x minus 2x. 8 minus 5 is 3, and then minus 2 is 1. And the answer is just square root of 3. And that, folks, is it. I will see you in class. Take care, and thanks for sticking with me.